Good morning. Let's start the last lecture in this term. It will be a little bit shorter, and then we will have discussion. Originally I planned for an exam at this time, but nobody has subscribed, so we do not have to examine it at the moment. Anyway, what I wanted to tell you is a little bit about displaying results. The important point is that all producers want the results to be very fancy, very nice, to look very realistic. On the other hand, computing results might be time consuming. So there is some balance between displaying really what is calculated and displaying fast what looks nice. And most of software producers unfortunately give higher value to the second thing, that is to displaying nice results. But remember, they are possibly not true. The story repeats. At the beginning, this was with circuit simulators at the times where my first PC had a clock frequency of 4.7 megahertz and some 500 kilobytes of RAM, which means that calculations were not as fast as today, so even simple circuits took time to evaluate at many frequency points. And now it was very important to present the result in a nice way. What I'm talking about, let's make an illustration. For example, let us have something which is like a transmission line, which is, let's say, 30 ohm, and it is a quarter wavelength at 1 gigahertz. And this line is watched from a 50 ohm system. So we have 50 ohm termination here, 50 ohm port here. So there is some reflection. And the reflection diminishes at a frequency when this is half wavelength, or 1 wavelength, to 1.5 wavelength. So the real performance, for example, of reflection at the input or output port, which would be S11, would look like, well, it would be 0 at 0 frequency, then it would be maximal when this is a quarter wavelength, so 1 gigahertz, that would be maximum, at 2 that would be minimum, maximum, minimum, so it would look like this. So this is the reality. Now imagine what happens if you would examine the circuit at only 0, 1 gigahertz, 2 gigahertz, 3 gigahertz. So what you get is something which looks very bad if you just get the data. No one displays only the calculated points. So the first point, what you can do is linear interpolation between calculated points. And once you see this, you would be probably aware that there are no circuits which have such sharp edges on a frequency characteristics of any kind. So you instantly see that this is a nonsense. And you would possibly add some frequency points. For example, with doubling the number of equidistant frequency points, you would get something like this, which is not that bad. But what if you choose, for example, 1 gigahertz, 3 gigahertz, 5 gigahertz, then you would have only those points, and the response would look like this when interpolated. And this looks realistic unless you know that this could not be the true, because a straight line is something that has a circuit which has this transmission. So this as a problem. In order to find out, I have one tip. If you display your results in complex plane, not as magnitudes but as complex numbers, this straight line would look like this. So at this point you know that you have a problem. You should increase the number of frequencies, and then you would really get the real response, which would look fine. So this is a problem. If you have some interpolation and you have very few points, you may get into troubles. On the other hand, a picture with such edges does not look very nice at shows and demonstrations. So the producers decide to make a little bit better graphs. Which means, for example, that instead of just making linear interpolation, the first tip is to use splines, cubic splines. Cubic splines are nice functions that, when used for interpolation of points, they have two important properties. First, they make it through all the points that are calculated, but second, there are no edges. They use two conditions. First, to run through all the points that have been found, and second, to be smooth. That is, the first derivative is continuous. And then you would get something like which is again not true, but it looks like true. I mean, once the curvature is smooth, you would think that this circuit really exists, that it might be true, and it will not trigger you to increase the number of points. Well, this all has been happening since the very beginning of computer-aided design programs like it, as touchstones or super compact PC, and we are talking now about possibly 40 years ago. Now, with field analysis like finite difference time domain or other methods, the computational effort has been many times increased. Yes, and the complexity of problems we can solve also increased very much. So still, even we have fast computers with big memories, we still have to somehow save computational time, or the producers have to do that in order to trick us to see their software as instantly running so that we would buy it. And now there are many more sophisticated tricks that you should know, that they are behind what you see. And in fact, what you see on the screen is not a result of field analysis that much. I will show you one of those important ideas which have some physical background, so they are based on a model which is real and possibly correct. But still, it may produce a problem to you. Again, the results and the things behind the scene start with old-fashioned circuit theory. As you remember, circuits like, I don't know, circuits composed of resistors, capacitors and inductors should have some transfer functions. And those transfer functions may be written for complex frequency, which then in fact gives you the reply both on the transient functions and frequency behavior. We would at the moment only think about frequency responses. So more or less a frequency response of such linear circuit would look like a fraction in which you have some coefficients in numerator and denominator. Let's say we have a function of a complex frequency, that's the j omega, and the function should in normalized form look like there would be 1 plus j omega divided by omega 0, and the denominator would be 1 plus j omega divided by omega 1. This would be a circuit of second order. It has 1 0 and 1 pole. More complex circuits could have several zeros and several poles, so that there would be more brackets in numerator and denominator. Given that the circuit is composed from resistors, capacitors, inductors, and transformers, its frequency response must stick to this form. Some of those frequencies here could be zero, which would result in having only a constant there. So I should possibly give there some complex constant. And now this is a real circuit that must have this frequency behavior, the transfer function. Now, how to use that to decrease the number of frequency points at which we calculate the behavior of a circuit. For example, we would use a moment method which runs the analysis at distinct frequencies. Each run at a frequency costs us some time, some computer resources. So how to decrease the time and get a good characterization of the circuit which is plotted on the screen? Well, so the algorithm mostly starts with the first part of this fraction. So it expects that possibly the circuit or the resonator, the body under test, is described by a simple transfer function, which has one complex constant and one pole and one zero. So there are 4 real numbers that characterize it. Real and imaginary part of the constant, and a zero and a pole, 2 frequencies. Now, the computer would do this. We have to examine the circuit from frequency omega 1 to frequency, from this would conflict here, so okay, from omega A to omega B. And in order to do that, we run the analysis at omega A and omega B. Let's say that we get 2 complex numbers. The transfer at omega A, real and imaginary part, the transfer at omega B, real and imaginary part. So we have 4 given values, out of which we can get 4 constants in this equation. So I will take this equation and fit real part and imaginary part of k at omega 0 and omega 1, so that the transfer function exactly fits in the data I have calculated. Okay, let's say I have 2 points here. Well, now I will find out one more point within the range. Let's say I will find some random point which is not very close to the beginning nor very close to the end, but it's not just in the middle, and I will calculate at a frequency omega c the transfer function. Let's say this is the value. Now I will calculate this using full analysis of the circuit, and I will calculate that as well using this simple equation, using this ratio, and there are two possibilities. I will get the same numbers or I will get different numbers. If I get the same numbers, I say, okay, my estimation of the circuit behavior using this formula is fine. So I will not test the circuit anymore, and I'm happy with it. Now, the user would get a nice plot of this equation on the screen as a result. Because this is a kind of transfer function that is common to electric circuits, it looks perfectly nice. I mean, it's believable. The second point is, the second idea is, well, okay, I get, using that fraction, I get this result, but analyzing the circuit, in reality, I get this result. Then I say, okay, this is not exactly the same, and I have to improve my model. Obtaining circuit analysis at this frequency gives us a complex transfer function, which is a real and imaginary part, so there are two elements in it, and that enables us to improve our estimation. So now, typically, I would add two more brackets, one to the denominator, 1 plus j omega divided by omega 3, and 1 plus j omega divided by omega 4. And I have a new approximation which should be better than the original one. And the process repeats. So I will randomly choose one more frequency, one more angular frequency, and test whether my fraction is a good approximation of the real performance of the circuit. If yes, I finish my work and display the result. If not, I will use the new values to increase the number of poles and zeros in my estimation. So this is a very simple idea which, in fact, tries to find an equivalent circuit composed of inductors, resistors, and capacitors, an equivalent circuit for the data I have simulated. Now, for electric circuits, that's a very good solution. For real field analysis, this is not that nice. I will tell you shortly why. For example, if you have a transmission line and you add there a stub, a portion of transmission line that is, for example, short-ended. So at a frequency where this is 1/4 of a wavelength, the short end transforms here as an open end, and the stop is not connected to this transmission line, or it works like if it was not connected for a harmonic state, not for a pulse, but for a harmonic state. So this is resembling the situation of a circuit, a resonance circuit, which is connected here to the line. So this is something which is more or less like a resonance circuit. So this would behave like a resonance circuit. Under the resonant frequency, this would behave like an inductor. Over the resonant frequency, this would behave like a capacitor. And at the resonant frequency, it would look mostly like an open end when seen from the transmission line. Based on a lossless line, it would be a perfect open end. But a circuit composed of a resistor, of a capacitor and inductor, would have but one frequency at which this would work. This stop, let's say at 3 times the basic frequency, would be 3/4 of a wavelength and would again disappear from the circuit. But this is not the true with this resonance circuit. So real behavior of a system of conductors and dielectrics may be more complex, and in wide frequency bands may not really resemble electric circuits composed of only resistors and capacitors. That is, distributed elements behave somehow different from lumped elements. And in that case, you might have different behavior of your circuit and your model. But by calculating more frequency points, the results would be close one to the other, and you might get good solution.